Okay, so what kind of data or statistics or questions might you have that would be appropriate for an outcome measure? There's two basic sets of questions or data that you are looking for about an outcome measure before you use it. One is its consistency, or what are its reliability errors, because all instruments have reliability errors. The second part is more complex and usually is an evolving idea, is the validity of the instruments themselves. And so by validity, we mean what are they actually measuring, or what is the right way to interpret those particular scores, and what kind of abstract ideas or concepts can we apply the scales to. So some examples of scales that have been developed for abstract concepts: kinesiophobia, self-efficacy, balanced confidence. And so we're looking for traits in the questionnaires that reflect those ideas. Right. And so let's start with reliability, and let's use two examples, one easier, one harder. We'll start with the range of motion and then delve into a self-report scale called the lower extremity measure. So some of the things we'd like to see about a test before we use it is what's the reliability. And so we have two different types of reliability. We have inter-rater, which is between two testers or two therapists or more, and then between the same therapist having performed it repeatedly. So both types are important for different reasons. The statistics that we would use for that are the interclass correlation coefficient. It's very similar to an R value that you might calculate in statistics class, like the Pearson, and it's used to calculate something called the standard error of the measurement. But the interclass correlation coefficient in and of itself as a correlation coefficient isn't that useful to us. It's an abstract kind of number that relates to how consistent the data is, and we usually think of values above 0.9 as being very good, but it really isn't that practical for us to use the statistic and then go to the whether or not to use the test. What we really need is we need an error estimate in the units of the instrument itself. So for goniometry, for example, it's really not useful unless you know that the errors are plus or minus 5 degrees. And actually, they're a little bit smaller for finger muscles and bigger for the hip, for example. But unless you know those, it's very difficult to apply the measurement clinically. And so the standard error of the measurement is the way we convert an interclass correlation coefficient to an absolute error measurement that we can use. And then the way we would interpret that is typically one standard error is a 68% confidence interval, so we usually use two. So two standard errors for shoulder external rotation is 5 degrees. So the way we would apply that clinically is at the start of a treatment, say if we were trying to improve external rotation, if we did some manual therapy and stretching and remeasured and the person only had a 44-degree post-treatment reading, well then essentially we would interpret that as there was no change in range of motion and the treatment was ineffective because it's not above air. So this is a nice graph that kind of illustrates some of the different levels of change that we're trying to assess. So first of all, there's no change, and that's below a standard error of the measurement. Okay, potentially detectable difference, and then there's a minimal detectable difference, which is the minimum change detectable beyond the threshold of error. And so again, I think that the distinction between standard error of the measurement and the minimal detectable change is not significant, except that the minimal detectable change is more conservative. Okay, so and then finally you have this change that's the minimal clinically important difference, which is defined as the difference in those who experience small but important changes. So the amount of change that's important for the patient to perceive a significant effect. And so you can see this is patient focused, these are measurement focused. So just can you detect a real change in that measurement? So these two, the standard error of the measurement and the minimal detectable difference, are essentially reliability issues, and then the minimal clinically important difference is a validity issue with the relationship with the patient and how they perceive a meaningful effect. So let's use now the lower extremity measure, which is a new questionnaire that was published by Jaglol and JBS in 2000, where they had over 30 items with a wide range of questions that was attempting to capture the concept of self-reported function. And so in this data, they had a reliability. So they said in our sample at baseline, the interclass correlation coefficient was 0.85. So it's an R value. So you can see that doesn't give you much of an idea of like how to apply that to a patient, because it's a ratio, which is the R value, right? So, and the measurement itself is called the LEM, or lower extremity measure. But when we go ahead and plug that in to these equations here for SEM, you have it, and you can see the equation here is a standard deviation times the square root of 1 minus the ICC. So there's the numbers. We get 1 SEM is 3.7, so that's a 68% confidence interval. So we multiply it by 2 to get a 95% confidence interval. And so our SEM is 7.4. So basically, so if we had a patient that that we measured a change of less than 7.4 points, we would assume that they actually functionally didn't improve at all. But if they scored higher than their pre-treatment score by a value of 7.4 points or higher, we know that their change in function, at least if their perceived change in function, is real. So now that we know kind of how to assess the minimal error, another thing is like a choice you have is like when you go to use the instrument, can you achieve that same level of error, and what kind of training and difficulty will you have in achieving that? And what you want to do is think about the different sources of problems that contribute to error. And so one of them is the instrument. And so in the first case, it'd be the goniometer. In the second case, it'd be the actual questionnaire you're using. And that may cause error independent of you or the patient. The second example is you, like, is it easy, in the first case, is it easy to place the goniometer or the arms of the goniometer, the axis, and then make the reading off of the goniometer. In the second case, it would be, is there something about the scale that you have to do to achieve a score? And that's one of the things about patient-reported outcomes that make them very popular, is that essentially if they're well constructed, the clinician or rater has almost no influence on the errors that exist. The final one is the patient. So if the patient has a lot of inconsistency in terms of the attribute you're trying to capture, so if it's pain, if the pain's widely varying, then if they fill out the questionnaire at this moment, but then it changes in an hour, then they're going to be confused on how to respond to the questionnaire. Another example is cerebral palsy and range of motion, where people with neurologic deficits oftentimes have wide-ranging range of motion, different times of the day. And so irrespective of how well you place the goniometer or how well you kind of execute the range of motion test, the patient themselves might vary significantly and result in an error between sessions. So those are the sources of error, and it's up to you to kind of think about the amount of training that it would take to execute the outcome measures without introducing error. So that's the short version of reliability errors, and so we're going to talk a little bit more about validity in a minute, but let's just give some examples of some